Hey guys, how's everyone doing?
Not too bad. How are you?
I'm doing all right. Um, switch this. I was just catching up with your homework. Our last week finally. So I think so we're basically done with all of the new material that we needed. So um, we'll just do a review. So we'll run through like all of the topics that we need. Um, And we can do some examples too, but I mean, if we have to study for the final, so there won't be anything new. If you have done all of the quiz problems and all of the exam problems, if you just look over solutions to those, you should be pretty well prepared for the test. Like the problems are going to be really similar to the quiz problems or exam problems that you already had, except for like the very last section that we did on like linear product spaces. So that's what we did last time. So there's one problem on that topic since we haven't really I haven't tested you on that yet. You guys have any questions before we start at your exams?
No, just excited to get this over with.
Yeah, I feel you. Holidays are nice. Yep. Yeah, just have 1 week left, so need to focus and then you guys can rest. All right, so we'll just kind of run through from the beginning like all of the topics that we did because it's been a long semester, right? And I mean, a lot of things we've been using, kind of, we've learned it and then we kept using it, but some things maybe we didn't really come back to as much. So we'll just kind of go through everything. Right? So kind of like we started with kind of solving linear systems. So I'm not gonna go through that. You guys all know how to solve linear system, right? And like row reduction algorithm. And we've been doing this all semester and looking at your quizzes, I think you guys all can do it. Right? But this is something that we already did in algebra. Kind of the newer things that you don't do in college algebra is we started writing things out kind of like in matrix form and getting more used to kind of going from like one form to another form, right? Like when we're dealing with matrix equations or matrix multiplication by a vector, right? We learned how we can write it either as like a linear combination of columns of A, right? Or if I'm looking at columns of A and putting them into my matrix A, that's the multiplication of the matrix by a vector, right? So that was kind of the things you don't do in college algebra, basically. And then we had a bunch of theorems that were kind of all of those statements are equivalent type of thing. So I tried to kind of summarize all of them so it's a little more organized, right? The first one was again just kind of the equivalence of when we're solving augmented matrices, right? So if I wanted to solve a system like AX equals to B, right? I can look at this as, I'm putting rows of A in the augmented matrix B and looking for solution X, but I can also look at it as if I do have a solution to the system. That means that my vector B on the right here belongs to the span of columns of A. And also that when I write down B as a linear combination of columns of A, this has a solution, right? So kind of all those three things are equivalent, right? And that was probably the new way to look at it, at least newer than something you do in college algebra. Yeah. So and then again we had all those like equivalences, right? So if for each B in Rm equation, Ax equals to B has a solution, right? That statement is also equivalent to saying that for each B in Rm, each B in Rm is a linear combination of columns of A. Now, or that the span of columns of A equals to Rm, right? Or that A has a pivot position in every row, right? But this is all kind of related to what we had on the previous page, right? Except now we're talking about how kind of my if this was my linear transformation, that linear transformation is on 2, right? I can basically find a solution for any vector b here. Now, you guys remember all of this? Oh, that was a long time ago. I mean, we've been using some of this, right? Like the pivot position in every row, right?
Yeah, it's
So,
pretty familiar.
huh?
Yeah, it's pretty familiar, so I think it's coming
Yeah.
back quickly.
Yeah. We're gonna can relate all of those guys. So and then we also did, so that thing with the project here haven't really came back to very much, but remember when we were talking about solving homogeneous and non-homogeneous systems? So for homogeneous systems, I mean, we kind of did a lot, but we never really came back to that fact about solutions of non-homogeneous systems and how they're related to solutions of homogeneous systems. All right, so homogeneous and non-homogeneous, there was just when I have 0 or when I have some non-zero vector b, right? And x equals to 0, like we talked a lot about it, like the null space is basically the solution, is basically all of the general solutions to the homogeneous problem, right? So all of the vectors x and Rn such that x equals to 0, right? We can write any x that belongs to the null space, right? The solution space of the homogeneous problem as like linear combination of some vectors that span the null space. And when we were finding those, I mean, you basically have to solve your linear system by a row reduction algorithm, right? And then the number of vectors in the basis for your null space are going to basically be equal to the number of free variables. Remember when we're solving, when you're finding solution for this, right? Even if you were, again, thinking about like the pivot positions, like if you're missing pivots in the columns, those would be your free variables, and each free variable will give you one more parameter, right? So they would end up being your kind of weights here, right? So number of free variables will give you dimension of the solution space for the null space of A, right? But the one thing we didn't really come back to is, well, if this was a homogeneous system, what I do if I just replace 0 with some non-zero vector b? How is my solution going to change? Right? And when we were solving those, we noticed that if I solve the homogeneous problem and then solve the non-homogeneous problem, the solutions really have one part in common. And that part is going to be the solution of the homogeneous problem. So for example, if I had this matrix here, 3 by 3, and I solved the homogeneous problem like Ax equals to 0, I would get that my solution vector, or basically null space, is spanned by this one vector for thirds 0 and 1, right, where alpha is some real number. But if instead I solved Ax equals to b, and also wrote down my solution in this parametric vector form, I would see that, well, basically part of this solution is going to be the same. I'm going to have the part that has some free variable in it is going to be exactly the same as the solution to the homogeneous problem. So the only new part of the solution is going to be this other vector, and this vector is not going to have any free variables. It's going to be fixed. So the structure of the general solution for this non-homogeneous problem is always going to be kind of summation of this particular solution. This solution satisfies in particular this non-homogeneous problem, and then plus your general solution to the homogeneous system. All right, so this will be true for all linear systems. And if you guys take differential equation, the differential equations, this will keep coming up quite a bit, because when you're solving those, you're going to have something very similar to this. You'll talk about like homogeneous and non-homogeneous problems, except you're going to be dealing with kind of like functions on the right-hand side. But I mean, you'll see this again. Do you guys remember doing this? Yep, I think you, yeah, I would print out or kind of put together all of your quiz solutions. So you should have, I think quiz 10 I didn't post yet. But at least like the earlier quizzes, just kind of maybe redo those problems or look through the solutions. because those would be something, the kinds of problems that you might see from earlier chapters. Like there isn't going to be any surprise problems from earlier chapters on the final. Any questions so far? All right. What's the next thing? So we talked about linear independence. Right? We kind of talked about it in two different chapters. Right? It's just at first we're only talking about linear independence for vectors in Rn. And then when we talked about kind of in general vector spaces, we could also apply all of those concepts to general vectors. Right, but kind of important parts about linear independence. I mean, one, you want to be able to show if the set is linearly independent, right? So by definition, the set is going to be linearly independent if you take a linear combination of all of those vectors, set them equal to 0, right? And if this only has the trivial solution, meaning that the only solution to this is that all of my weights have to be equal to 0, then the set would be linearly independent. Right? If I can find some constants that are not 0, right? x1, x2, xp, even if it's just 1 that's not 0, then it would be a linearly dependent set. Right? So I'm kind of, if you have a 0 vector anywhere and you set it, automatically makes it a linearly dependent set because the coefficient of 0 does not have to be equal to 0 for this equal to 0. So again, you can kind of write this in different ways. You can kind of write it down as a linear combination, or you can write it down as kind of augmented matrix form. Right? You can even like solve it as a homogeneous problem. Right? So if you're looking at it as a homogeneous problem and you're looking at your vectors as columns of A, right? Then you're looking for columns of A being linearly independent and things like that, right? So kind of other things to look for when you're trying to show that the set is linearly independent, right? If you have those vectors as columns in your matrices, right? You want to look for, you don't want to have any pre-variables for linear independence, right? Why? Because if I do have free variables, that means that my homogeneous problem has a non-trivial solution, right? But for linear independence, I need to have only the trivial solution, right? And then also the pivots, right? But for this, I need to have pivot in every column, right? So kind of in every column for linear independence and in every row for being onto, right? All right. What else do we have here? Yeah, I guess you also have these theorems that if I do have a linearly dependent set, that means that, there is some vector somewhere in this set. It could be one vector, it could be more than one vector, but it's at least one vector somewhere in the set that makes everything linearly dependent. All right, so we had this theorem that said that, well, if it's linearly dependent, then I keep going through my set one by one vector until I get to the one that makes things linearly dependent, or until I get to the one that can be expressed as a linear combination of the preceding vectors. Right? So this was useful to us when we were trying to kind of make linearly independent sets, so construct bases for subspaces, right? Because if you have a set, then you don't know if it's a basis, but you can kind of take the first vector, one vector is linearly independent, take the second vector, are they multiples of one another? No, the first two vectors are linearly independent. Take the third vector. Is the third vector linear combination of the previous two? No, then you can take the fourth vector, right? And so on. So that's what we use that theorem for. All right, and also it's kind of it's a good theorem to explain kind of like this linear dependent condition, that it's not that kind of like remember in orthogonal set, like all of the vectors are kind of mutually orthogonal to one another. With linearly dependent sets, it's not that they're all linearly dependent on one another. It's just there's probably like one or more vectors that are linear combinations of the other ones. And all right. Now it's linear independence, dependence, and then we have linear transformations we talked about. All right, and again, we talked about it in a few chapters. And thing with linear transformations, it's a very, very general concept, right? So not all linear transformations can be expressed through matrix multiplications. I mean, the majority of linear transformations are not matrix multiplications. It really all depends on which vector spaces you're working with. Like if you had a infinite dimensional vector space V, you can't write it down in terms of like n by n matrix, right? So for matrices, you really need to kind of be operating from finite dimensional vector space to finite dimensional vector space. And then you can at least rewrite kind of your transformation in terms of like the matrix representation, right? But again, not all linear transformations are expressed in terms of matrices, right? But what's true about all linear transformations is this one condition, right? I basically have this function that kind of takes an element of one vector space and brings it to another vector space. But the only two conditions that I need to have for it to be a linear transformation is that transformation of the sum is the sum of the transformations, and that transformation of multiplication by a scalar is scalar times transformation. Right? Those are the only two things you need for something to be linear transformation. And then from just those two conditions, you have a lot of other, like the important other properties is that linear transformations always map 0 to 0. And I mean, this is just kind of like both of those in one, right? If I have two constants and two vectors, right? T of alpha u plus beta v is alpha t of u plus beta t of v. All right, so I mean, that one is kind of what you're using in practice usually for kind of two or more vectors and constants. Now, some definitions that went with our linear transformation. So the domain of a transformation, I mean, this is my vector space V, right? It's just all of the, this kind of the set of all of the vectors from which I'm taking my x's in order to map them with my transformation T, all right? And then when we're dealing with like null spaces, I mean, you can say null space of T, but I mean, usually, I mean, you guys will probably see it if you take more math classes. Another name for null space would be the kernel. Like when you're dealing with linear transformations, you usually say kernel of T, which basically would be an equivalent of the null space of a matrix or a null space of the transformation. It's like all of the values here in V that my transformation T would map to 0, right? It's kind of like null space. And then on the other side of this, where I'm getting the image of my transformation T, I'm kind of taking stuff in V and mapping it to W. So W is kind of my destination. So W is the codomain. But codomain is not always the same as range. So the range of the transformation are actually all of the values that I'm getting here when I'm kind of mapping all of the values X and V and applying T to it, right? So it's my range is not always going to be, range is going to be a subspace of or subset of codomain, but it's not always going to be my codomain. All right, but the range is basically right, all of the B and W that such that T of X equals to B for all X and V. Right? So those are kind of important. And then the range also, if I'm dealing with matrices representing linear transformations, then my range is the same as the column space of A, right? So yeah, so T is represented by the matrix. Again, for first, we basically only worked with Rn and Rm, right? So all our linear transformations were transformations that mapped Rn to Rm. And I think you have to look at like, I mean, I posted those notes, but you should have kind of a good resolution of all of this in some of your, I think it's like week 3 or week 4, some of like earlier week modules, right? So when we're looking at kind of how do we construct matrices for linear transformations, right? If I know that my linear transformation is expressed by matrix multiplication, right? How do I go back and forward from transformation to a matrix? So we derived the formula that basically a matrix that we use for linear transformation consists of columns where each column is basically how does my transformation affect the unit basis vectors, right? So E1 like 1, 0, 0, right? E2 0, 1, 0, 0, and so on, right? And so with that you can get, I mean, you have a table you guys can use it. You know, I mean, it's good to remember how to derive them all, but I mean, you can look at your little table of all of the transformations, right? You have like different reflections. You have kind of reflections in kind of 45-degree line, reflection in axes. You have those like shearing transformations, right? You have, you know, like shrinking and expanding transformations. So, I mean, if you do have problems on a test for it, I mean, I do want you guys to be able to kind of, again, like go back and forward between matrices and transformations. So if you see a matrix for a transformation, something like this, I know that my columns are going to be, this is what transformation does to E1, and this is what transformation does to E2. So it basically takes my unit vectors 0, 1, and 0, right? And just makes the x coordinate negatives and basically takes this vector and makes it -1 and 0. Right? You guys remember doing all this? I'm remapping this. And so basically my t of 1 and 0 is -1 and 0. Right? So and basically you can construct your matrix. Everything that good linear transformation does is defined by just knowing what it does to those two basis vectors for your space. So you want to be able to construct those matrices, and also since we do know how to do matrix multiplication, you can actually pretty easily deal with kind of a bunch of different transformations nested one on top of the other. So for example, I mean, this was from your midterm 1 problem, right? And you had to basically write down the matrix for a transformation, which basically had 2 parts. So first, you want to rotate all points by pi/6 radians. And then second, you want to do a shearing transformation. And then what you want to do is you want to basically write down the matrix for both of those things combined, right? And I mean, first you can just get matrices for each one of them, right? So for the first one, for rotation, again, you're looking at, I mean, what am I doing with my kind of unit basis vectors for R2 since I'm on R2, right? If I'm rotating by pi/6 radians, then, right, this vector gets rotated by pi/6 and E2 gets rotated by pi/6, right? But you can just use some trigonometry, right? So the unit vectors is kind of like you're in a unit circle with trigonometry, right? So kind of my new coordinates for 1 and 0, because this vector would move over here, are going to be cosine pi/6 and sine pi/6. I just kind of think of the unit circle quantities. And for the second one, again, from trigonometry, think of the unit circle, you have minus sine pi/6 cosine pi/6. You can put it all in the matrix and get your values. Now, And then for the second one too, so it's already giving you what it does to the first and the second unit vector. So you can just put those as, write them in your vector form and put them as columns in your matrix. So the only thing I noticed, I mean, a lot of you did fine on the midterm 1 for this problem, but it was the order of multiplication that most people kind of messed up a little bit. So why am I multiplying the second one over here? Like if you think of it, I'm taking value x, right, in some space. I am applying first, I am first applying rotation, right? So I have my T2 of x, oh no, this is my T1 of x. All right, so my next point is T1 of x. This is the point that I just rotated, all right? And then to that, I'm going to apply my second transformation, all right? My T2 of whatever I had here. So my resulting point is going to be T2, T1 of x. And in terms of matrix multiplication, right? If this is multiplication by A1, and this is multiplication by A2, right? I'm going to have A2 times A1. So kind of your second one will be multiplied on the left. I think that's kind of the one thing that a lot of you didn't do correctly. Does that make sense, guys? And I mean, sometimes like it's symmetric and it doesn't matter in which order you do it, but I mean, in general, it matters which way you do this. Right? I just kind of think about this picture. I'm applying my rotation first, and then when I'm doing shearing transformation, I'm taking like the stuff that I already rotated and applying the shearing to it, so that matrix A2 is going to multiply kind of on the outside. Does that make sense? Yeah, these questions. So I mean, something like this could be a good problem for the final, because you're kind of constructing matrices and things like that. But again, it's something that you already have seen on your midterm. So kind of go over all of the midterm and quiz solutions. All right, so again, we're still on linear transformations, and now we have kind of some properties of them. And again, we kind of mostly did this for transformations from Rn to Rm. But again, all of this stuff works for kind of general vector spaces, right? So we have two important properties. We had transformations that could be onto and transformations that could be one-to-one, right? And I mean, some transformations could be both, some could be neither, some could just be one, right? But that property of onto meant, again, we could restate it in different words, right? But it basically means that if I'm looking at, I mean, all it means is that my range equals to my codomain, basically. Right? If I'm mapping everything, if I'm taking everything from Rn and applying my linear operator, then I'm covering all of my codomain. So range equals to codomain. Or you can say that for every b in my codomain, every b is going to be an image of at least one x in the domain. All right, so something like this is not onto and this is onto. In terms of if I was using matrices, onto means that the span of columns of A equals to Rm. All right, so I'm covering all of the codomain. And then one-to-one was a little bit different. One-to-one was more to do with, do I have kind of like this uniqueness? Like I don't want to have kind of two different values in a domain mapping to exactly the same value in the range, right? I want to have like unique value mapping to the unique value in the range. Right? So again, you can restate it in that for each b in Rm in your range, is an image of at most one x, right? So, you know, I mean, you've seen this in algebra too, like this one-to-one property. Like it's important when you start doing inverses because you don't want to have like an inverse transformation of B, and then you have two different options here, right? You want to have kind of like Y maps to B and B maps back to Y. There's no other value. Now, all right. So yeah, for all B in Rm, T of x equals B has a unique solution or no solution at all, right? In terms of solutions of linear systems. All right, so no solution at all if, you know, I'm not saying that I have to take B in the range. I'm just taking B in the codomain. So if B is not in the range, then your Tx equals B has no solution. But if B is in the range, I should have unique solution. And we can also relate this to homogeneous problems too. All right, if T of x equals to B has a unique solution or no solution, your T of x equals to 0, so the homogeneous system only has the trivial solution. So that's probably the more common criteria that's used to show that something is one-to-one. That your transformation is one-to-one if homogeneous problem only has the trivial solution. And in terms of columns of A, if I am representing my linear transformation by a matrix, one-to-one property is equivalent to having your columns being linearly independent, right? So onto columns span Rm, but one-to-one is equivalent to columns being linearly independent. Makes sense? Just remember this stuff. What is a lot of things? Just gonna go back and organize everything. So now we did a bunch of kind of this matrix algebra, right? We learned how to multiply matrices, multiply vectors by vectors. We learned about like transposes. I think you guys remember all of this stuff. And we learned how to kind of like rewrite different matrix multiplications. If you multiply matrices, we had some rules to remember that multiplication of matrices is not commutative. Formulas for multiplying matrices, right? The ij term of the matrix, have a formula how to represent it. But I mean, in general, for your problems, I mean, if you have to multiply matrices, you just always do your row by column rule, right? So just remember how to multiply your matrices. I think you guys are all good with that. So we learned about transposes of matrices, right? Transpose basically, I'm taking a matrix and what used to be rows becomes columns, right? In terms of my indices, it's just switching indices I and j, right? And we had some rules for transposes, like to undo the transpose, you just transpose again, and then transpose of the product, I can distribute it, but I have to switch A and B places. So AB transpose is B transpose times A transpose. I should remember all of those rules. Then we moved on to inverses of matrices, right? So inverse of a matrix, and I mean, inverses would also be defined for only square matrices, so n by n, right? And it's basically a unique matrix that acts as, the multiplicative inverse, right? So we can't do 1 over A, so we're doing A to the power minus 1, right? So A inverse times A is identity, and identity is A times A inverse, right? It's a unique. So it's basically an equivalent of like 1 over A for real numbers goes to 1. Now, and how do we find inverses? If you have 2 by 2 matrix, I mean, you have a nice little formula, so you don't have to do too much to get an inverse, right? So just remember the formula. You're looking at your quizzes, it looks like some of you using the formula, but you're not using the right formula. So like make sure, just, I mean, you can make a little, I mean, if you take an exam at home, right, you can make yourself a little cheat sheet with all the formulas. You don't want to lose point just because you copied the formula wrong. Right, so for inverse of the 2 by 2 matrix, I mean, the way I remember it is I switch this diagonal, so this becomes D, this becomes A, and then make off diagonal elements negative. Right, so I'm switching A and D and making B and C negative. And then I have to divide everything by my determinant. Right, so we talked about determinants in later chapters, but determinant was the scalar quantity that told me if the matrix is invertible or not. All right, so here, all right, if AD minus BC is 0, then I can't divide by 0. My A inverse is not defined. All right, but if this is not 0, then I mean everything is defined and my A inverse exists. All right, so for 2 by 2 matrix, just use the formula. It's the easiest way to do it. But if you start getting 3 by 3, 4 by 4 matrices, then this becomes more difficult to find inverses. And the way we were doing this, probably like the easiest way to do is, I mean, you do have to do your elementary row operations, right? You form your augmented matrix, A and identity, and then do your elementary row operations until A is then exactly in reduced row echelon form or becomes I, right? And if A is invertible, it will be row equivalent to I, so you will be able to do this, right? If you run into problems along the way, that probably means that your matrix A is just not invertible. We have some formulas for inverses, like A inverse is A, right? Inverse undoes the inverse. Just like with transposes, A B inverse is B inverse A inverse. You have to switch them. And then you can kind of interchange in inverse and transpose. A transpose inverse is A inverse transpose. You should remember those few rules. And we have this big invertible matrix theorem. Right, again, you just have to remember that all of those things are equivalent. And some of those things are kind of equivalent in themselves, but here what kind of unites all of those things is also the fact that A is a square matrix. A is not just M by N, A is N by N, it's square matrix, right? Because I mean, it doesn't make sense talking about inverses if I don't have a square matrix. I mean, you could define this for like right inverse and left inverse, but we're not doing this here, right? So it's just for square matrices, and for square matrices, a lot of things kind of collapse like to be the same thing. So like even if you just look at pivot positions, right? Kind of having pivot position in every column is equivalent to having a pivot position in every row, because now you have same number of rows and columns because matrix is n by n. Now, but I mean, yeah, all of those guys are equivalent to matrix being invertible. So you have n pivot position, you have this row equivalence of A to I, you have that homogeneous problem only has the trivial solution, right? Which makes sense because if A is invertible, if I have my problem, AX equals to 0, and I multiply by A inverse on both sides, right? A inverse times A is I, so I have I times X. A inverse times 0 is just 0. So X equals to 0 is my unique solution. Then the same thing with B, right? If I had AX equals to B and A is invertible, so A inverse exists, the same way I would have A inverse B. This becomes I. Not anymore. It becomes I, and this becomes A inverse B. So X has a unique solution that's given to you by A inverse times B, right? So a non-homogeneous problem has a unique solution, and homogeneous problem only the trivial. Right, I mean, it's all just consequence of, if you have an inverse, you can basically solve it as as you do it with just real numbers. Yeah. Oh, and then all the other things, right? Your Also, if A is invertible, then it represents a linear transformation that's 1-to-1, and also a linear transformation that is onto, so it's both onto and 1-to-1. All right, your columns are linearly independent, your columns span Rn. You can also show that your rows would have to be linearly independent also if A is invertible. Unique solution. Columns form a basis for Rn. I don't know those things like column space is Rn, right? Rank of A is n, null space is 0. That's related to your homogeneous problem having only the trivial solution. All right, so kind of throughout the whole semester, we're doing like a little bit of everything, and then we're putting everything together to see how everything is related. You guys all good with all of these concepts? Yeah. Questions? Yeah. So if you like, yeah, if you look at all of the problems you guys did for quizzes and midterms, kind of like with everything summarized, you can see that there's a couple of ways to do something, right? If you were trying to show that like columns of a span Rn, for example, like you don't necessarily have to do this directly. You can kind of use any one of the other things. Like you can show that, you know, if I put columns of A in a matrix, that matrix is equivalent to row equivalent to In, or look at the pivot positions or something like that. All right. So what is subspaces? So subspaces of kind of general vector spaces, and then also subspaces. I mean, we did a lot of Rn and Rm, basically. And so some things that we don't need to prove that it's a subspace, something that's always going to be a subspace, are basically kind of three big things. So one was, if I take a span of any number of vectors in Rn, it's always going to be a subspace. The span of any number of vectors is a subspace. Also, the whole of Rn is a subspace of itself. So it's the biggest subspace of itself. And then zero subspace would be kind of the smallest subspace. All right, so you kind of go from Rn to different spans of vectors to zero is the smallest subspace. All right, and then you can also get subspaces when you kind of dealing with your matrices, like null space and column space are also always going to be subspaces. All right, I mean the null space is basically a span of your solution vectors. So it's going to be a subspace also. And then column space is the span of columns of A, right? So it also kind of is a subspace by construction, it's the span of vectors. But I mean, we proved all of those guys are subspaces, but if you have to prove, if you're asked, if you're given a set and you want to prove that it is a subspace of Rn, I mean, one, it has to be a subset first, right? But for subspace, what you need is you need to show that it's closed under addition, that it's closed under scalar multiplication, and that zero is necessarily in that subspace, right? So you can have subsets of Rn which don't include zero, for example, and those aren't going to be subspaces. Subspaces have to have zero, and they have to be closed under addition and closed under multiplication. So again, like subspace and subset is not the same thing. Subspace is a subset, but not all subsets are subspaces. They have to have those conditions. So this is for Rn, but then we also can kind of apply this to general vector spaces, right? So for example, you can have a subspace Pn. Pn is polynomials of degree at most n. So Pn would be like a subspace of all continuous functions, of a vector space of all continuous functions. Or you can look at like P2 is a subspace of P10. They're kind of nested in that way. But again, all of those concepts of vector spaces and subspaces, it's not just the Rn, right? And it doesn't even just have to be finite dimensional spaces, because if you look at polynomials of degree at most n, I mean, yeah, this is going to have dimension n plus 1. right? But if you look at all continuous functions, that would be an infinite dimensional vector space, right? Right, so I mean, you guys are all good with finding null spaces and column spaces, yes? I think I've given you a few problems like this. I mean, for null space, you always have to, unfortunately, do all this row reduction algorithm, right? To find how many free variables you have, right? Label them, express everything in terms of this linear combination of your solution vectors, and those would be basis for your null space. And for column space, I mean, you also want to bring it to some echelon form and then identify the pivot columns in your echelon form. But then say if you have columns like 1, 3, and 5 in echelon form, then you go back to your original matrix, and then the same columns are going to be pivot columns here and there, right? But in echelon form, you just get the numbers of the columns, and then you go back to A and pick corresponding columns of A, and those would be the basis for your column space of A. Right? So it's, I mean, you've had like, I think you had quiz problem, and you had a like another exam problem where you have to find null space, find column space, and you find the row space. Right? For row space, just take like non-zero rows, right? In the echelon form. You guys are good with that, yeah? Questions? All right. So basis, we did a lot with basis. So I had we had a kind of a bunch of little theorems here, but kind of to put everything together, I mean, what makes a set of vectors a basis? We have basically two conditions. If I'm taking the span of those vectors, that equals to H, my subspace, and not only that, I want them to be linearly independent. So the basis vectors is a linearly independent set that spans the subspace, right? So it's kind of like the smallest set of vectors I need in order to be able to kind of generate any vector in that subspace, right? And for that, I need this linear independence, right? So then dimension of the subspace was the number of basis vectors. And then we had some theorems, so like sometimes you know what the dimension of your subspace is. If I have a subspace of dimension P, I already know that I need P basis vectors in my basis. So in that case, you don't have to show that, you don't have to show both of those conditions. If you have P linearly independent vectors in a subspace of dimension P, then it automatically will be a basis. So they're linearly independent. That would imply that they're also span this and it's a basis. Or if you know that you have P vectors in the dimension P subspace, and you know that they span the entire subspace, then they would have to be linearly independent to automatically be a basis. So kind of if you know the dimension and you know you have P vectors on your set, you only have to check one, linearly independent or that they span, and that would be a basis. Right? And kind of also another consequence of this was called the basis theorem, that if you have any subset of H of more than P elements, it would have to be linearly dependent, right? Because you can't have, right? You can have more than P linearly independent vectors in a subspace of dimension P, right? Because then there would be a basis, and then your dimension would not be P, it would be bigger than P. Now, so that's another criteria you can use to show something is linearly dependent. Like if you have a set of 3 vectors in R2, they have to be linearly dependent, right? You can't have like 3 linearly independent vectors in dimension 2 subspace. All right, so what do we do next? So you had what's called unique representation theorem also. So that was when we were basically taking vectors in some general subspaces and basically taking the basis for those subspaces and then expressing those vectors in terms of linear combinations of basis vectors. So our unique representation theorem told us that basically those weights that I'm assigning to my basis vectors have to be unique for each x, right? And we used our beta coordinate mapping. All right, but basically this was again just rewriting of, x is the linear combination of basis vectors with weights P1 through Cp. So I'll rewrite this as matrix multiplication, where my matrix here just consists of columns that are my basis vectors, and then I'm multiplying it by this column vector, which just contains all of my weights, right? So this was my beta coordinate vector, right? X beta is just the weights assigned to beta vectors. All right, so we did that. We talked about like rank and nullity, right? Dimension of column space and dimension of null space add up to n, right? And then another big theorem we had was the spanning set theorem. Right? So that theorem basically allowed us to, if I have any set in a subspace, basically what this theorem told us that if it's not linearly independent already, then what I can do is I can reduce the number of vectors in the set in order to generate the basis that's linearly independent, right? So basically what that allows me to do is kind of go through the set of vectors until I get to the one vector that's a linear combination of the previous ones, right? And if it is, then I can just delete that vector and my span does not change, right? So like I went through to some vector vk. Vk was a linear combination of v1 through vk minus 1. I just deleted it, right? And my span is still going to be the same. And so you can keep doing this, keep deleting those vectors that are linear combinations of the other ones until you get to a linearly independent set that will still span this S, and therefore it would be a basis for S. So this spanning set theorem kind of gives us a way to generate a basis, right, for this, for S. And also we showed that, if I have some subspace and it's not a zero subspace, then I would always be able to find some subset of that H that is a basis for H, right? So all subspaces will contain bases within themselves. Like we would always be able to find a basis. And so like those theorems. The one we have change of coordinates. So those are also good problems to review. All right, so what do we do with change of basis? Right. And you can just kind of like write down all of your little formulas, like to study for the test if it's hard to remember. All right, so when we were writing down our kind of coordinate transformation, again, we're starting with basis for Rn. Our change of coordinate matrix, right? So basically the columns are just my basis vectors in Rn. And you can kind of use it in one of the other ways, right? I know that PB, my change of coordinate matrix, is invertible because since those are my basis vectors, columns are linearly independent, so this matrix is invertible by invertible matrix theorem, right, and so on, right? So my X was equal to this matrix times the beta coordinate transformation, right? Again, it was just the rewriting of linear combination. And if I multiply this by P inverse on both sides, right, P inverse, this will become I, this will become P inverse times X, right? So you can also basically solve for your weights assigned to basis vectors by multiplying vector X by P inverse. And we kind of use this a lot when we're dealing with like polynomials, right? You want to show that, say, like set of polynomials is linearly independent, or you want to find like weights associated with particular bases. Kind of using the fact that my coordinate mapping is also linear and one-to-one and onto transformation, I can actually just take vectors from some general vector space and then transform them to more familiar Rn and then transform them back. So that's what we were doing here to say solve this problem, right? If I have those three polynomials, I want to show that they're linearly independent, right? I mean, I could do it from scratch too. I mean, you're still just applying you're writing down the linear dependence condition, right? So what if I multiply all those three by constants set to 0? I need to show that all the constants are 0. But instead of kind of using polynomials, what I can do is I can take my beta coordinate transformation of both sides of this, where I'm using beta, my kind of standard basis for polynomials of degree at most 2. And if I do this, I can use linearity condition, right? I can basically factor out constants, right? Beta transformation of the sum is the sum of beta transformations. And doing this, I don't have to rewrite polynomials anymore. I can just put kind of, I can just use the three-dimensional vectors where each component is coefficient of different power of t, right? So I have 1, t missing 0, 2, 1, 0, 2. I'm just replacing them with corresponding vectors. So, I mean, this is why we were able to do this, because of this transformation being linear and one-to-one. All right, so this allows us to basically transform problems where I'm dealing with general vector spaces onto kind of solving them in Rn and then going back with your conclusion to this vector space. Those ones, I think we did all of this. It was like midterm 2. Like look over those like polynomial problems on midterm 2. Right, and then we also did kind of change with other kind of changing from some basis to standard basis, but we can also kind of go in between two different bases, right? If I have basis beta and basis C, right? So kind of two different bases for the same subspace or vector space. There's kind of two ways to deal with this. How do you go from one or the other? I mean, really was like two ways to compute how to do this. So like the general formula. So if I have my coordinate vector of x with respect to c and coordinate vector of x with respect to beta, all right? So here, this matrix basically changes beta coordinates to c coordinates. And in order to do this, so this matrix was consisting of columns where each column is going to be my original basis v and kind of destination coordinate vectors of that. All right, I'm kind of going in the opposite direction. You're just replacing b with c. All right. So, I mean, generally, you just have to get one of them, and then the other one, you can just take an inverse, right? Because kind of going from, I mean, what are you really doing with this? You can take vector in v, transform it to Rn with beta vectors, or you can transform it to Rn with c vectors, with basis c vectors, right? But, you know, maybe you use beta, your friend used c, but how do you communicate? Well, you can communicate between different bases of Rn with those matrices, P beta to C or C to beta. So, and again, like there's a couple ways to do it. You could, to compute your kind of change of coordinate matrices, you could have put in this augmented matrix form. So, I mean, it's pretty fast. The only problem with it is like it's sometimes hard to remember. You kind of like rederive it to remember which one goes where, right? But yeah, you can basically start with, if you're going from beta to C, right? You put beta vectors here, C vectors here, C to beta, like that, and do elementary row operations until you basically have your C vectors become I, and then your V vectors will become P beta to C. But I think the most straightforward way to do this is because you already know your like x is PB, x beta, and x is PC, xc, right? You can just rewrite one of them for x of c. X of c is PC inverse times x, right? Just multiply by P inverse of c. and then just plug in the second x here in terms of beta, right? And you have PC inverse P beta for you, P beta into C, right? So now it's a lot easier to remember how to compute those matrices, but you can do whichever way you want, right? Again, you have the midterm problems like this, and with problems like this. So kind of go over this, make sure you know how to do those problems, right? So, for example, if I had two basis vectors, basis beta, right, B1 and B2, another basis C1 and C2, right? So I have two different bases, and I want to be able to convert between basis beta and basis C, right? So again, kind of some notes here, like what could make it easier. Like you don't have to do both of them. So I mean, you have to find both P beta to C and PC to beta, but you don't have to do this row elimination on both of those, right? You can just do one of them and then compute the other one by taking the inverse. It's going to be faster, especially if you're dealing with 2 by 2, right? But which one do you do first? Like over here, if I wrote down my beta to C, so I have kind of beta vectors here, C vectors here, and then C2 beta, my beta here and P here. I want to convert this to I and whatever my P is going to be. And so over here, my numbers are kind of ugly. I have like -7 and 9. All right, so I want this to be 1. So if I divide by 7, this is going to be fractions here. Over here, it looks a lot easier. This is already 1, right? So my row elimination is going to be easier for putting B first. So maybe I'll compute P C2 beta first because it's easier to do row elimination without the ugly fractions, right? I'm getting my PC2 beta is 5364. And then what I'll do, I'll just take the inverse, because if this is C2 beta, then beta to C is the inverse of C2 beta. And then I'm going to get this. That makes sense? So just kind of just look at it, like examine your vectors to see which one is easier to do. Over here, I didn't want to deal with fractions, so I just did the PC2 beta first. And then once I did that, I took an inverse. All right. Or you can just use your formulas, right? If you do your multiplication, I mean, you know your PB and PC. I mean, those are just matrices populated with basis vectors, right? B1, B2, C1, C2. 2 by 2, I can compute inverse of this. So then P beta to C is PC inverse P beta. Multiply two matrices and you're done, right? And I mean, you can take the inverse of this now, or you can, again, just multiply. That makes sense? All right, so we have the whole chapter on the determinants. With determinants, I mean, what do you need to remember how to do? I mean, obviously you have to know how to compute determinants. We're using them in the chapter on eigenvalues and eigenvectors and things like that. Like it's a good way to show that a set of vectors is linearly independent or not. So you want to be able to compute determinants, and kind of the general way to do this is by this cofactor expansion, right, which with formulas. So remember this. There are shortcuts for if your matrix is triangular. So triangular would mean that it's, I mean, you have, something on the diagonal, but either everything below the diagonal is 0 or everything above the diagonal is 0. That would make it a triangular matrix. All right, so for triangular matrices, determinant is easy. It's just multiplication of all of the diagonal elements. All right, so you can have a little shortcut. And then another thing we did is, we could also compute the determinants by doing those elementary row operations and kind of keeping track of how the determinant changes when you do elementary row operations. Because if you're if you're adding multiples of rows to other rows, your determinant is not going to change. right? So you can do those operations and not changing determinant, or if you're interchanging rows, you have to change the sign on the determinant. And if you're multiplying rows by something, you can think of it as you can factor out a constant from any row outside of the determinant. So, I mean, this was another way, but I mean, in general, people usually use your cofactor expansion, right? But I mean, that was like another alternative way to maybe mix the two to get the determinants. So you kind of like do your elementary row operations to bring your matrix to a triangular form where determinant is easy to compute, all right? But keeping track of how the value changes. So then some of those properties, right, of determinants are also definitely need to remember, right? So kind of part of the invertible matrix theorem, A is invertible if and only if determinant is not equal to 0, right? And then transpose doesn't change the determinant. And then kind of very important property here, determinant of the product is product of determinants. That actually simplifies a lot of calculations. So we should remember this property. Determinant of the product is product of the determinants. So now we did a bunch of basically different applications, right? So we did Kramer's rule, we did formula for A inverse. So I mean, those two guys are good for basically getting some general formulas for either solutions of systems or inverse matrices. Like if you had some variables maybe inside of your matrix A, this gives you a nice way to just kind of write down the formula for the solution, right? Without doing elementary like row operations and row reduction. You're just basically getting the formula in terms of the determinants. Right, so we did some problems with this on the test. And then we also did applications with like computing like areas and volumes, like the area of parallelogram. No, I don't think, probably not. I mean, I've tested you on this, it's just applications. So I'm not gonna put, like on your final, you're not going to have those, like the volumes I'm not putting on the final. So just kind of know how to do Kramer's rule, right? And know how to compute determinants and know how to use those things. Okay. So like if, for example, I wanted to find, I think you had like a midterm problem like this, determinant of like a to the power 10 or something like that. I mean, you don't have to compute a to the power 10 and then do the determinant, right? What you can do is, this is determinant of a times a times a 10 times, right? If determinant a b is determinant a times b, what you have to do is compute determinant of a and then bring it to the power 10, right? So kind of remember how to use this rule. But I mean, this stuff is important, but like don't worry about it for the final. So that was basically it for kind of midterm 1, midterm 2 stuff. So obviously everything we did for review for midterm 3. I mean, we pretty much just did it, so I'm not gonna go through it. Like if you go to your final exam module, I attached the like, review notes for midterm 3, so I'm gonna go through that. I think I've graded a couple of midterm 3s so far. So as you guys working on your midterm 3, I'm going to grade it and send you the solutions to midterm 3. All right, so I'll try to, I mean, I'll go through some new incoming midterms today. I mean, I'll try to kind of like keep grading it quickly, but yeah, so once you do your midterm 3, I'll send you the solution for it if you want to study from it. But otherwise, look over like the review notes for midterm 3. So, and then the only other thing that I did not test you on, and that was kind of like the only section that we did past midterm 3 material. So it was 6.7, the section on inner product spaces. I think that's your last homework. If you're doing your online homework, it's really short. There's like 5 or 6 problems on it. So I would try to look at those. We'll look through lecture notes. But I mean, what do we need to know from the inner product spaces? It's really nothing new. It's just, again, kind of like we had our dot product, right? The inner product is kind of a generalization of the dot product. The dot product is defined for 2 vectors in Rn, right? But the inner product would be is something that's defined on the general vector space. And all it has to satisfy is kind of those conditions, right? It has to be like this function assigned to 2 vectors in the general vector space that's commutative, that you can distribute, you can factor out constant, and then if you take inner product of vector with itself, it's going to be greater or equal to 0 and only equal to 0 if u itself is 0, right? And so with those conditions, you can actually generate a lot of different kind of functions for those inner products. So the one that we've used in this chapter mostly was kind of, again, dealing with those polynomial spaces. So if I have a vector space of polynomials of degree at most n, I can define an inner product on this space by basically evaluating polynomials at some like n plus 1 distinct real numbers. So basically having a formula for my inner product of those 2 polynomials as, you know, there's first and second polynomial evaluated at t naught, first and second evaluated at t1, and all the way to tn, right? So we showed that this is always going to be actually satisfying all of those conditions, right? And kind of like the important part here is not any number of points. It has to be that n number of points if you're dealing with Pn, polynomials of degree at most n, like you do have to have n plus 1 points, because you really need to have this condition, u dot u equals to 0, if and only if u equals to 0. So if you don't have if you have less than n plus 1 points, you won't be able to use this condition that, so if this is 0, then you're ending up having a polynomial that has more than n zeros, and by fundamental theorem of algebra, like it has to be 0, right? So kind of like the number of those points is important. It's related to Pn, right? But we showed that this will satisfy all of those conditions, basically. And I mean, just for your test here, I mean, you guys will see a lot of those inner product spaces if you're doing like engineering and taking like more math classes, like applied things. But for now, I mean, it's still kind of new concepts. So just, you know how to use. I'm not gonna give you any new type of inner product, but like this one we've used a lot. So I mean, I could give you a problem where you have to work with this inner product, right? But otherwise, like all the things we did with dot products, we can do with inner products, like our Gram-Schmidt, right? Our projections, we can like flip through that chapter on inner products, right? So all of those, like the Gram-Schmidt process, you're just replacing your dot products of vector with those inner products. Your projections, you're replacing your dot products with inner products. I mean, everything is the same. It's just now you're using this product instead of the usual dot product in Rn, right? And for doing this one, it's actually easy kind of to notice if you look at the structure of this, right? It almost looks like a dot product, right? But you kind of like multiplying P to Q evaluated at T naught, P to Q evaluated at T1. So you can actually, when you're dealing with those polynomial functions, you can write them down as little vectors of evaluations, right? Like what is it at T naught, what is it at T1? So for example, if I have P5, right, the polynomials of degree at most 5 space, and I'm going to define an inner product on this space as evaluation at -1, -1/2, 0, 1/2, and 1. So those are my T naught all the way to Tn. Now, So how do I write my vectors here? So if I had u of t, actually this should have another one. It should be 4. Oh, it's not. Should be 4. So I can basically look at this inner product and say, well, if my u of t was equal to t, right? What is my u of -1? What is my u of -1/2? What is my u of 0? What is my u of 1/2? And what is my u of 1? Right. And then if I'm looking at v, I have v of t equals to t cubed. Right. And then again, I'm just going to look at the vector where, what is my v of -1 and so on. Right. So this would be -1 to the power 3. Right, -1/2 to the power 3, 0 to the power 3, 1/2 to the power 3, and 1 to the power 3. All right, and then my dot product, well, my inner product here is really just dot product of those two vectors. You can kind of, this kind of like a fast way of dealing with this. All right, so I mean, it's kind of like an example of the types of problems you may see on the test or on the quiz. All right, so that's the last thing we'll do today. All right, so suppose I have standard basis for P3, polynomials of degree at most 3. So my standard basis would just be my different powers of t. Now, and starting from this basis for P3, I want to construct an orthogonal basis for P3, who is basically using my kind of inner product defined as evaluation at -1, -1/2, 0, 1/2, and 1. All right. So again, just remember how you did this with dot products. Now, instead of dot product, you're just doing this inner product, right? And I mean, it's kind of easier to try to rewrite them as those vectors, right? Where basically it's just kind of the function 1. I'm evaluating at -1, -1/2, 0, 1/2, and 1. All right, I'm just evaluating like t evaluated -1, -1/2, 0, 1/2, and 1. T squared evaluated at those numbers, and t cubed evaluated at those numbers. So just kind of write down those vectors for evaluating those guys at -1, -1/2, 0, 1/2, and 1. All right, because then when you start doing your Gram-Schmidt, all right, if you take the first one, the second one, P0 and P1 are orthogonal already because their inner product is 0. So now you just have to use your Gram-Schmidt to generate the P2, your third vector, right? And just like with vectors in Rn, right, you basically taking the next one in the list, P2, and then subtracting the projection of this t squared onto the subspace spanned by the previous vectors. So you only take in the orthogonal component of t squared to those two vectors, and just kind of using your inner products. All right. So just kind of compute those here. T squared inner product with 1, t squared inner product with t. All right. You can do those on the bottom here. All right, and kind of fill in. So again, just Gram-Schmidt, just with inner product defined this way. So, and we're getting our P2 is t squared minus 1. All right, so I have P0, P1, P2, those are orthogonal. And if I want to get the third one, I have to kind of do this again, right? But I'm taking the last one in the list, 3, and I'm going to subtract from t to the power 3 the projection of t to the power 3 onto the subspace spanned by the previous 3 vectors, right? So including that t squared minus 1. All right, so again, but it's just your Gram-Schmidt process, right? But you're doing it with the different inner product, like not with a dot product, but with this other inner product defined on the space of polynomials, right? But otherwise, everything is pretty much the same, right? Compute your inner products, and here you have your orthogonal basis for P3, right? And remember, like this is orthogonal basis with respect to P3, but it's orthogonal, kind of keeping in mind that the orthogonality condition is written in terms of this inner product. Yep. That makes sense? And then if you do have an orthogonal basis, right, for P3 now, there's other things you can do with it, right? So in particular, remember we did like the best approximation. So if, for example, I have orthogonal basis for P3, but I have a function P of t is 2t to the fourth. So t to the fourth is not in P3, it's a higher order polynomial. But maybe for whatever reason, I mean, I can only really operate with functions from P3. I can't do anything with higher order polynomials, but I do need to kind of represent this somehow. And what I want to do is I want to find kind of the best approximation to this polynomial of degree 4 by polynomials of degree 3, right? So I want to find the best approximation for this by polynomials of degree 3. And we can use our projections here, right? So all I'm going to do is I'm going to take this polynomial of degree 4 and then project it onto polynomials of degree 3 by taking this projection onto n of my orthogonal basis for P3. So I want to have my orthogonal basis here, and then if I project it onto my orthogonal basis, and then again, it's just using the formula, right? I'm taking projection onto 1 here, I'm taking projection onto t here, I'm taking projection onto t squared minus 1 here, I'm taking projection onto my t cubed, right? So, and then you can just, I don't know, it's going to be a little long, right? Then, but again, you can just compute everything and find your best approximation for that. I didn't finish that one. You guys have any questions? I have a lot of, we mostly just kind of went over all of the topics a bit from the beginning. So it's what we did today, and then also review notes for midterm 3, right? So don't forget to do that. I posted it in your final exam module. And then again, just go over all of your midterm solutions. Right, you have your midterm 1, 2, and 3 solutions. And then your quizzes with 10. So quiz 1 through 10 solutions. Yeah, just go over all of those. If you know how to do all of those problems, you're not going to have any problems on a test. I mean, a lot of the problems on the final exam are just going to be pretty much problems from the midterms or quizzes, just with different numbers or values or something like that. So know how to do all of those. You kind of like go through all of the theorems to remember stuff. So midterm 3 and quiz 10, those last two, I didn't post solutions yet, but as you guys are doing them and I'll grade them, I'll send you the solutions so you can study from it. Because I made them due, I made midterm 3 and quiz 10 due like pretty much at the very end. So I'm not going to post solutions to it like in the module, but I'll send you a solution once you finish the test or the quiz. All right. Any questions, guys? Yes? No? Everyone's doing good?
Nope, I think I'm ready to do that final.
Yeah. So I think like next time, what we can do is we're kind of finished reviewing. So I think maybe yeah, next time. So next class, we'll have a Zoom class, but you know, I'm just going to be there to answer your guys' questions. And I mean, one option is I mean, when you take exam in class, like sometimes you don't, maybe you like don't understand like the wording of a problem, like you can ask me during the test. So I mean, what you can do is you can actually take the test, start taking the test during our regular class time. Next time. So I'm around, but I'll find some time to kind of just like be on Zoom in case you guys have more questions. So I'll post something today. Yeah. Alrighty, but
Thank you, Professor.
otherwise, good luck. No, see you next time.
Have a
Okay.
good afternoon.
Thank you so much.